Hey everyone, welcome back to our third example practice problem where we're going to walk through the very first version of a full spectral assignment for a given molecule. So this is a little different than the examples we've done previously where we had to choose between two molecules. Here we have the molecule, we know exactly what it is. Our task is now just to take every piece of data that we have and assign it to each of the carbons and each of the hydrogens on our molecule. You're going to have to do kind of a combination of the two for your post lab. You'll have a choice of two isomers, but whichever one you choose, we're going to ask you to do the full spectral assignment for. So let's dive in by taking a close look first at our one-dimensional data, and then we'll look briefly through the two-dimensional data, finding cross peaks and correlation signals, and just kind of tabulating them all up so that we can get a sense for what data we have, and then we can start to put the pieces in place. Now, this is the strategy that I like to use. If it feels better to you to start diving into the one-dimensional NMR and immediately making some labels on the structure as you go, feel free to do that. Like I say, there are a ton of different ways to approach these problems, and you want to choose the way that's going to work best for you and your lab team. Let's start with our 1D NMR data, and you can see we have two spectra on this slide. Yeah, you might be a little confused about what those are. They're both 1D data, and they look very different because they're on different scales, right? So the top scale on that axis is in hertz, right? So that's why the numbers are so much bigger, and the bottom scale is in ppm. That's why they're different, but the top spectrum is really just a zoom of the bottom spectrum of interest. This kind of region, I'll sort of draw it in with these blue lines here to show, oh, okay, what we're really looking at is just an enhanced bit of this small region of our full NMR. So the bottom one represents the full spectra that you would see if you were at the NMR computer taking a spectrum, and it represents all of the peaks of importance. So we should go through these and just kind of highlight some important thoughts. Think about what they might mean based on their chemical shift, and also thinking about integrations and splitting. So on the big spectra to start with, you can see that there are two major peaks that don't end up in our zoomed in region at the top. And so that's this one here around 10 and this one here at about 4. So those are wildly different chemical shifts, and we might have some idea already before I even dive in as to which protons those could be. So let's talk about where we see a shift of something so high like 10. 10 ppm is way higher than you see for almost any other protons. Aromatic protons are really not going to get much past 8.5 ppm at the highest. So what the heck could be all the way up at 10? It has to be something that is really strongly de-shielded by the environment around it. And if we look at our reference molecule up here at the top, there is one proton that may feel pretty obvious because it is sort of out there and labeled for you as a top contender here, and that's going to be this proton here. Why is it so downfield shifted? Well, that is a characteristic of the functional group of the aldehyde. So you can either just keep that in the back of your mind, or you can also think back to our anisotropy cartoons and picturing the carbonyl having a shielding region on top and on the bottom, but in the plane it's strongly de-shielded, and that's where that hydrogen atom sits. So that's what's happening up here at about 10 ppm. Just because that chemical shift is so distinct, I think we can go ahead and label that proton already. But for these other ones, we may not really have such a clear idea, so I'm not going to label many of them as we go along. We just want to say that this is our CHO proton. That's how we abbreviate aldehyde, is CHO. And the other thing that we know about this is that since it's not blown up, there's nothing else for us to see here. It definitely is a singlet. And because we know which proton it has to be, we already know what its integration is, which might come in handy later on when we're evaluating some of these other integrations here in the middle. We know this has to just correspond to one hydrogen because there is only the one. Okay, on the other end of our hydrogen spectrum, we have something a bit lower at about 4 ppm. Everything else is in that kind of 7 to 8 range. So what the heck could be at 4 ppm? When we talk about signals that are in the upfield region, we think mostly about alkane chains totally saturated CH single bonding motifs. I don't want to say nothing interesting, but the less interesting functional groups that are mostly based on carbon and hydrogen and don't have a lot going on nearby. So you might say that about the rest of this entire molecule because there's only one heteroatom oxygen, but the rest of it is aromatic save for one piece, and that is this piece right here. That's the only sp3 carbon that we have. And so those hydrogens are going to be very different from all of the sp2 hybridized aromatic and aldehyde protons that we see. So those almost certainly have to be down here at 4 ppm. And because we know that there are two of them, that'll give us a little bit of information. So we're going to call this the CH2 because there is only one CH2 on this molecule. We are seeing that as a singlet again because we don't have any zoom to tell us otherwise, and it has no adjacent neighbors, so we wouldn't expect it to be split. And we know that that has to be a 2 hydrogen peak because there are 2 hydrogens there. So we've already got a couple of pieces knocked out. That's really great. You may go through these and have absolutely no idea what any of the protons are to start, and that's okay. You just have to work through the pieces as they come up and start to make more sense to you. Luckily, this one had a couple of easily identifiable pieces that we can use as handles for us to figure out the other ones that are much less clear. So now let's dive into this zoomed in region here, and keeping in mind that all of these are somewhere between 7 and 8. We don't have the ppm values nicely picked out on the top spectra, but we can kind of roughly read them from the bottom spectra when we want to refer to them later. One more thing before we dive into this more complex region. I tried to show as best as possible that the region kind of starts here and ends here. And that is to say that it does not include this peak here. Why not? Why don't we care about that? Why isn't it picked out with an integration? That's because that is our solvent, our deuterated chloroform. And it's not actually the CdCl3 because you can't see deuterium in the proton NMR. It's the small residual amount of CHCl3 that's contained in the solvent. So that doesn't have anything to do with our molecule. It's just how we prepared the sample. So we're going to completely ignore those peaks for our analysis today. And just if you see something that doesn't seem to be labeled, it doesn't seem to match up to anything on your spectrum, just do a quick sanity check and say, is that my solvent? Chloroform comes in at 7.26 ppm every time. So if you see a peak there that doesn't quite make sense, it's chloroform. I've tried to do my best to label all of those solvent peaks for you in your post-lab assignment, so hopefully there is no confusion. So now that we've kind of taken account of these strange outlier, extreme, one side or the other peaks, and we have a good idea of what they are, before we dive into the more complex, kind of weird looking zoomed in region, I want to do something that will hopefully help as we go through that process, but will definitely help later on. So it's something I would recommend that you probably do very first thing. I got a little bit ahead of myself wanting to label these interesting other peaks. You want to make sure that you give these peaks a label or some kind of a name, something that you can refer to them as, because we might know about the aldehyde peak here or the CH2 peak here, but the other ones we don't necessarily know what their identity is yet. So we need some way to talk about them. So again, just like the previous two examples, I want to do this by lettering my protons and numbering my carbons, starting at the highest ppm. So let's go ahead and put those alphabetical labels in here. I'll do it on both the full spectrum and the zoomed in region. You want to start at the very highest shift with A, then B, C, D, E, F, and G, all the way down at the bottom. So our zoomed in region only accounts for B through F. Let me translate those labels up to the top as well. All right. So now to dive through this region of B to F, again, we may not have a real solid grasp on, oh, I know that signal has to correspond to this position on the ring. For the other ones, like I say, it was pretty clear cut, but B through F are going to be a little bit trickier, and that's part of the practice of this assignment. So since we can't necessarily nail them down on the structure itself, let's gather as much information from the 1D that we can about them so that we can start to make some predictions, make some observations, and think about where they might belong to start to narrow it down. So looking at peak B, let's just think about the peak shape and see what that tells us about B. It looks a little broad and lumpy to me, but I can't really see anything else happening at B. So I would characterize that as a singlet. So we'll just label that here. And then let's just go along and look at the peak shapes of all the other ones, and then we'll come back and talk about the integrations last. If we look at C, again, a little bit broad, but I would again characterize that as a singlet, whereas now we look at D, D definitely looks more like a doublet to me, as does E. And then we come to F. What is going on at F? It's kind of, I would classify this as basically a hot mess of weird peak splitting. And so because of that, we're not going to be too concerned with you telling us the very, very fine detailed exact type of splitting that's happening here. If we had maybe higher resolution or a bigger zoom, we could get a better idea. But since we don't, what we'll do is we'll just call this M for it's a multiplet. There's multiple different kind of peak splittings going on, and it's a little hard to tell what's what. To me, it kind of looks like maybe these are two triplets that are smashed together, and then they might have some fine degree splitting happening as well. But again, we're not going to ask you to get too specific with that. All right, so we have some peak shape, and that'll tell us some information about potentially neighbors and number of neighbors. But the other thing is, how many hydrogens do they correspond to? Since we don't have the same scale for the top and bottom spectra, we can't get out a ruler and measure the integrals, which is how they did it back in the day and how some people still do it today. What we can do instead is use more of our straight edge tools and techniques from either if you have iPad software, if you're using Google Slides or PowerPoint, we can use those to our advantage. So because we know some information on this full spectra at the bottom, we know that the aldehyde proton has to only correspond to one proton. There's only the one. So that integral must equal 1. And similarly, we know that the CH2 corresponds to 2 hydrogens, so that height of integral must correspond to 2. So what we can do is just draw a nice straight line along the bottom here that's going to match up with the bottoms of all of our integrals. And then if we simply copy that one over and align it with the top of the integrals, we now have a little kind of height chart that tells us which integrals correspond to 1 proton and which correspond to 2 protons. So if we think about B, D, and E, they all seem like they are matching up with the top of the 1H kind of meter, and C and F seem to match up with the top of the 2H sort of meter line. And that you may be able to get a feel for by eye in the top spectra here, thinking about the top of peak B's integral and the top of peak C's integral. It looks like about twice as much, but this full spectral way is another way to go about finding that data. So I'm going to transfer these integral annotations to the top spectra, and then I'll get rid of these orange lines because it's kind of a lot to look at. So we said that B is 1 hydrogen, C is 2 hydrogens, D is 1 hydrogen, and so is E, and F is 2 hydrogens. Great. Okay, so we'll remove those extra annotations. And now we have a really good suite of one-dimensional data that we can start to think about how we might assign B through F. Again, we may not know for sure yet, but let's just use some of the information we just pulled out to help start making some predictions. So if we look at B and C, those are both singlet peaks. So we would expect B to have no nearby neighbors and C to have no nearby neighbors. So probably one of those peaks corresponds to this hydrogen here, which has no immediately adjacent neighbors. Can we tell which one it is right off the bat? No. You might get a sense that it is more likely to be B because B corresponds to only 1 hydrogen, whereas C corresponds to 2, but we can't necessarily say that for certain yet. But because it has no neighbors, it's probably going to be, one of those peaks is going to be at that position. Similarly, if we think about D and E, they're both doublets, so we would expect that D and E each only have 1 adjacent neighbor that splits them. So looking at our structure, we could say, oh yeah, this position here has only the one adjacent neighbor to it here. And likewise, that position also has only the one neighbor adjacent to it there. But can we say for certain which one of those is D or E off the top? Not really. It's further complicated by the fact that if you look here and here, each of those positions already also have one neighbor. So it could be any of those four positions that correspond to D or E. We can't really tell yet. Then we come last but not least to the strange multiplet signal at F for 2 protons. So we're expecting that that is going to be 2 protons that now have definitely more than one neighbor and maybe more of a propensity for some kind of strange fine degree splitting to happen. So looking at that and what we have kind of remaining on our structure, we'd expect to see that position and that position having more than one neighbor and maybe more complex splitting going on. So we'll think about all of those positions, kind of keep them rolling around in the back of your mind as we start to analyze the other data. So if you're anything like me, you may find it a little difficult to just keep all of this information rolling around in the back of your mind while you're trying to analyze the other spectral data that we've given you and just thinking about the other assignments that you have for other coursework going on right now. I understand. It's a lot. So what I would recommend is if that feels like you feel like I can't keep it all straight in my brain, what I would recommend is just taking some notes as you go along, and it can be on the slides, it can be on a separate piece of paper, whatever works for you, to say, oh, okay, when I looked at this proton data, these are the observations that I made or conclusions that I came to. So I noticed this, and this peak was, 2 hydrogens at, ppm shift, and it was a singlet, so that means no neighbors. Stuff like that. So that way, if you're going along and you're making some notes about the data that you're seeing, then you can always come back to them later if you need a break and you want to come back to it at a different point. That way you don't have to start from scratch in catching yourself all the way back up with the data. You got some kind of cliff notes to go back to so that you don't have to start from scratch every single time. And I'll tell you that most of you will probably not just sit down and whip through one of these assignments in 5 solid minutes. I know that I can't do it that fast. So you will likely need to take breaks, walk away from it, and come back to it later. That'll help keep you and your lab group caught up all together, especially if you have a way to share these notes that you're making with each other. And then you can bounce ideas back and forth or come back to it. Sometimes you just need to walk away from a problem, think about something else, and then come back to it later. I know I get stuck in a rut sometimes like that, and taking a break really helps. So definitely feel free to do that as you work on these longer, more intense problems. So with that, we've got all of our nice labels in place. Now let's move on to talking about our carbon data. So here on this next slide, we have our one-dimensional carbon spectra, and you may have noticed that we have, again, more than one spectra. You may not have expected to see this, but we provided you a little bit of extra data for this one in order to help you figure out the difference between some of these different carbons. So you'll see the 3 spectra that we've provided are the kind of quote-unquote normal proton decoupled experiment. That's just any average carbon that you've seen. And then we also have the depth information here for you, the 135 and 90-degree depth experiments to help rule in or out different types of carbons as far as their hydrogen count. So let's roll through all 3 of these together, and then we can start to look at the 2D information. So let's just start with the proton decoupled spectra. And again, first thing first, before I get ahead of myself, let's label these with some numbers. So we have quite a few carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is down there, 11, 12, 13, and 14. So we just put a little break in the spectra here because most of these are higher up in the aromatic region and there's not really anything happening from like 120 down to 40. So that's the same spectra, just split apart for convenience sake. So do a sanity check here, check to make sure that it's 14 carbons. I won't bore you by counting them out loud, but I'm going to count them on this spectra just to make sure that I didn't miss any. Okay, I get 14. I think we're set there. So with all 14 of our carbons accounted for, now we can think a little bit about the chemical shifts and what that means. And then we'll move on to the depth data to get a little bit more information. So thinking about chemical shifts here, we again seem to have two outliers up here above 190, and then this one that we had to kind of cut off so that you could see it at a very low ppm around 37. What might these be? If you are thinking back to the analysis we did for the protons, you may already have an idea that if we have
A carbon that is really, really strongly downfield shifted.
that often corresponds to a carbonyl peak. And of course, we do have one carbonyl carbon at our aldehyde. So that is almost certainly our aldehyde or our CHO carbon. And then what about carbon 14 way, way upfield at about 37 ppm? Again, low chemical shifts correspond to just kind of carbons without too much else interesting going on. And the only other non-aromatic and non-carbonyl carbon that we have is going to be this one here, our CH2. So that is almost certainly our CH2. We can confirm that in just a moment when we look at the DEPT data. So let's do that. Let's look at our DEPT data. As we go from the proton decoupled to the 135, we see two different changes. So recall this from last fall. If we have any quaternary carbons, they disappear. And if we have any CH2s, they switch to a negative phase. So looking around, we see that carbons 1, 7, 8, 9, 10, 11, 12, 13 are still here and still look normal, but we are missing these 6 carbons. They've disappeared. And last but not least, we see over here on the upfield end that this peak has gone into the negative phase, but still appears in the 135 depth, which means for certain this must be our CH2 peak. But I don't think we're too surprised by that. It seems like the only one that it could be by chemical shift anyway. So there we go. We know carbon 14 certainly is a CH2. Now, we don't necessarily know the identity of 1, 7, 8, 9, 10, 11, 12, 13 just by their appearance in the 135 depth, because in the 135 depth, what we still see as positive phase peaks can either be CH carbons or CH3 carbons. We need to go from the 135 to the 90, where the CH3 carbons will disappear. So if you are looking ahead, you'll know that we don't have any CH3 carbons. We don't have any methyl groups here. So nothing's going to disappear as we go from the 135 to the 90. So we see the same faces here again, that all of those same CH carbons are still there. And again, we can think about this to do a little sanity check, that if we have this CH, emphasis on the H, O, there definitely has to be a hydrogen attached to that carbon, so that checks out for our aldehyde. And a lot of the rest of these on our molecule are aromatic with one aromatic proton off of them, so we're going to have a lot of different CH signals from our carbon NMR. Again, as you're coming up with all of these conclusions while working through the data, it wouldn't hurt to again, continue to make a list. You could say, oh, don't forget about 2, 3, 4, 5, and 6 all must be quaternary, blah, blah, blah. Make some other observations about whatever else you see, just that you can keep it in the back of your mind or share it with your lab group. So now that we've looked at the one-dimensional data, we can start to move on to the two-dimensional data. Again, I'm going to do this in a manner where I just go through all the data, see what there is, but I'm not going to try to really label anything too strongly just yet until we have all of the pieces to look at together. Now that we've gone through the one-dimensional carbon and hydrogen NMR, we can take what we've learned forward and start to look at the COSY and HSQC data to start to see some correlations between hydrogens and hydrogens and carbons. So let's start with the COSY, but before we actually look at any of the peaks, let's keep in our practice of making sure that we label things really well before we get started so that we know what it is we're looking at. Unfortunately, it's a little harder to see what's happening with these peaks here because we're just zoomed further out. We'll do the best that we can as far as labeling, but we won't be able to see the splitting as well, and we'll have to be pretty careful when we're in this region here because a lot of these lines are pretty close together. We're going to have to do some fine detail work to make sure that we're seeing the correlations as carefully as possible. So here we go with our labels. A, B, C is this tall one, D is that small doublet just to the side of C. E, F, that one is chloroform. Don't forget that's from the solvent that we talked about earlier. And then G is this last one. Same thing here. So we have G, chloroform, F, E, D, C, B, and A. And just double checking to make sure that you've got the right assignments there based on the ppm shift. Sometimes I've seen different data that will arrange the scales differently on either side. So just make sure that you're checking, okay, yeah, A was about at 10 ppm and it is here as well. Okay, now that we've got all of our labels on, we want to put in our identity diagonal so that we can ignore all of the peaks that fall underneath that because we know that those are not peaks of interest. I'm going to actually take my pencil size down a little bit so that I can make these lines nice and fine to not cut through anything unintentionally. This graph looks pretty square, so I'm going to try to draw from corner to corner, again, knowing that that won't always work on the first try. Let's try to arrange it. Oh, so that's pretty close. My iPad software had it kind of jumping back and forth, so I'll see if I can adjust this a little bit, but it doesn't really. Oh, there we go. Okay. I like that a lot better. So now we can see the things that are just totally cut off and we don't care about because they represent an identity coupling of something to itself. We can just ignore them. Everything else, though, we can't ignore. We need to make sure that we take account of. So what I'm going to do for this, as I have in previous examples, is draw a thin straight line and then kind of move them over so that I can see the cross peaks. This one will be another where I draw a lot of lines and then try to just fill in the cross peaks and get rid of the lines because they're just a lot to look at. So to get started, I'm going to read the top half of the graph and work down and then across to the opposite side. So we're going to kind of cut through some of these other peaks. It may get a little bit confusing, but if it helps you to just think that we don't care about any of the peaks that are in this bottom half of our graph, just ignore them completely. That may help simplify a little bit of the massive amount of data that we're going to look at. So I'm just going to try to start at this top corner and draw a line straight down, trying to get that as matched up as I possibly can with the straightness of that axis. And then I'm going to just cut this and move it over so that we can start to line it up with some of our cross peaks. We can see that if we follow this down here, this is the AA self-identity. There's nothing else that we need to worry about there. So I'm just going to slowly move it over until we get to here, where it looks to me like we have a peak right about here and one that's very close to the identity diagonal right about there. So there's two that kind of fall underneath there, and we'll talk about what their correlations are in a moment. I want to get all of my lines in first. So I'm going to remove those annotations and start filling in some extra lines. Copy another one of these over and try to pick up this peak here. Let me draw that in with a circle. I'm trying to pick up this peak here because that one is not one that we've caught yet. If you're thinking about, oh yeah, it also intersects with this one, you're right. But again, since that's in the red highlighted region, we don't need to identify that peak. It's already actually identified right here. So don't worry about that one. We're just going to worry about this one that is still currently circled. But I'm going to get rid of that circle so we can move on to another line down here. That looks like it's intersecting this small peak up here and also this off diagonal peak down here. Okay, so I think that's all of them so far. This COSY kind of looks like a lot, when you stop to think about all of the dots. But when you cross out the identity dots and you ignore those red highlighted dots that are redundant information, we actually don't have that many cross peaks here to identify, which is good. That means our job is going to be a little bit easier. Let's go ahead and draw some horizontal lines so that we can see over to the side, and then we can label in those correlations and start to think about them a little later on. So drawing another line here, try to get that as straight as possible, and then we'll move it along. And it looks like we have a couple of peaks here that are correlating back to this side to G. So we'll leave that line there. And then we'll paste another one in so that we can see all of the other correlations that we need to. So there's 2 there. I think we need one more to get this little tiny baby cross peak here. That looks about as good as I think I'm going to get it. So you can see why this very last cross peak here, I'm going to circle it, is a little tricky, right? Because it seems like it could kind of line up with either C or D. So I think that it's lining up with C. And I think that'll be a little bit more clear when I can remove some of these annotations. So I'm going to label it as a C correlation peak for now, but we can always come back and edit that later. Definitely make a note while you're working on these to say, these 2 peaks are close together. If things seem suspicious or we're having trouble getting to our final assignments, maybe come back and reevaluate this particular point. Okay, so now that we've got things where we think they should be, let's go ahead and label all of these cross peaks to see what they tell us. So I'm just going to start near the top. You start wherever you like. It looks like, and I'm going to actually adjust these lines a little bit here so we can see them coming all the way up to the 1D spectra. It looks to me like this peak here corresponds to B on the top and G across the side. So I'm going to write that this is a B to G cross peak. Similarly, this peak here is also in line with G, but it lines up with E on the top. So this is an E to G. Let me draw a better G there. E to G cross peak. And then if we follow down, I'm going to follow down along this B line here to this tricky one that's very close to the identity axis. And I'm going to say that that is a B to C correlation. Again, let's put a little star by that to say we got to come back and make sure that's C and not D later, just in case. So it looks like the other correlation we have here is coming down from either D or C. It's a little bit hard to tell. And then across to F. So I'm going to start off calling this one, I think it's closer under D. So I'm going to say for now that this is a D to F correlation. And the one here next to it, since we're getting a little cramped, I'll use an arrow, also looks like it corresponds with F on the horizontal, but it corresponds on the top or the vertical to E. So I'm going to call that an E to F correlation there. So when I remove these lines, you may be able to see some of these details a little bit more carefully. But before I do, just looking at this DF and EF peak. So now that we think we have our cross peaks pretty much figured out, I'm going to go ahead and erase these lines, or at least most of them. I do want to leave 1 or 2 so that I can double check that cross peak at BC, just to see if we can make sure that it is C and not D. So I'm going to remove most of these lines, but leave a couple so that we can kind of narrow in on this particular cross peak a little bit more carefully. So I'm going to zoom in a little bit more on this region of interest, just so that we can look more carefully at these peaks right in that central region and line up with C and D. So prepare for a zoom. This may feel a little bit uncomfortable if you get sensitive to certain types of visual change. There we are. Now we're zoomed in a little bit closer so that we can start to see a little bit better the alignment on the side C or D. So the vertical line at the top is coming down from B, and like I said, I think it's going over to C. But let's just go ahead and pick this
horizontal line up and kind of move it over just out of the way so that we can look at the identity diagonal for a second. If you look here in that region, we have kind of a lot going on. We have what looks like two peaks on the identity diagonal and then two cross peaks that mirror one another. What I'm seeing though is that this peak here is actually two peaks right next to each other. It kind of looks like one circle is here and the other one is butting up right next to it. So that's what I'm seeing there. And I think that has to do with the close nature of C and D on our axis. So if I bring this green line back in and try to line it up with C as carefully as possible, it looks like C corresponds to that bigger portion of the blob on the identity diagonal, whereas if I move over to D, that corresponds more closely to the center of the smaller, slightly upper blob on the identity diagonal. And now it doesn't really look like it goes to the center of that circled cross peak. So that's why I'm contending that this one that's starred is indeed a BC cross peak. The other thing that we might want to look at while we're zoomed in a little bit more closely is this cross peak here, because we said we weren't really sure if that was D or C. Let's look at that one as well while we're here so that we can rule it in or out. Again, let's move our horizontal line up here so that we're right in the middle of our F peak. And then I'm going to scroll up toward the top so that we can adjust our vertical line and read it a little bit more carefully there. Okay, so bringing this line over now and zooming back into our region of interest. So what I'm seeing is that this cross peak that I've labeled D here seems to line up with the center of this smaller portion of the cross peak, which we agreed based on our earlier analysis corresponds more closely to this D peak here and not so much to the C peak. So I am feeling pretty good about the assignments as I've labeled them right now. But this is what you should do if you're having a little bit of trouble deciphering, is that C, is it D? If they're close together, do whatever you can using a computer, tablet. If you need to print these out, just zoom them in using anything like PowerPoint, Microsoft Word, or Google programs as well to make the image bigger and really zoom in on some of these small fine grained detail pieces. I apologize that we can't make the resolution any better, but at least you'll be able to see a little more carefully than you will if you had this zoomed all the way out. So I'm going to zoom back all the way out now and get us centered back on our page. So now that we've kind of confirmed to the best of our ability those cross peaks, we can just go ahead and think about what they might mean to one another in space. So specifically thinking about G, we said already that G was probably these two protons right here. We can see that G has a couple of cross peaks that show a correlation between it and B and E. So B and E are probably pretty nearby to those G protons. And if that's the case, we want to be thinking about them probably being here or here on our structure. So I'm not going to make any formal assignments at this point, but that's kind of the way that we want to start thinking about what this COSY might tell us. And then if we know which protons we think are here or here, we can look for other correlations that would go around this ring and go around this ring to help us assign the rest of our protons. So we'll come back to more analysis on that after we first take a look at our HSQC data. So let's move down there, shall we? The last, but certainly not least, piece of our 2D data and our data overall is the HSQC, where we're going to be able to see which carbons are bonded to which hydrogens. And because we have kind of a forest of peaks going on here, it's kind of a lot, we have a nice zoomed in region given to us there in the middle, which corresponds to that set of peaks right there. So we don't have to strain our eyes too much because again, you can see some of these peaks are forming little almost snowman formations where they clump together very closely. We need a zoomed in region to be able to differentiate between them. Before we dive into this nice zoomed in region that's going to give us a lot more clarity about which protons go with which carbons, let's make sure we put our labels back in so that we know what's corresponding to what as far as carbons and hydrogens. So we'll label the hydrogens first again with letters. Don't forget that one is chloroform. And then we'll number the carbons starting with 1. I'm going to use even a finer pencil point because we have kind of a whole lot going on in this forest of peaks all at once. And we'll try to differentiate them on this side, but they're going to be, I'll do a better job of it here where they're a little bit more clearly separated. So we have 1, 2, 3, and 4 very close, 5, 6, 7, 8, 9, 10, and 11 are basically on top of each other right here. And then we have 12, 13, that's chloroform, and 14. Whew. Okay, we did it. So now let's finish up by transferring the remaining labels to this inset so that we know which ones those are. So it's a little hard to tell with the carbon NMR at first, but we're starting at around 130 on that carbon axis, which is about here. So it looks like this forest of peaks is what we're viewing in this inset. So I believe this is 7, 8, 9, 10, and 11, like I said, very close together. And then 12, 13, and clearly 14 is so far off on its own, we don't need to see that. As far as the hydrogens go, we have A is not pictured on this inset because it's very clear what that is correlating to. We don't need to zoom in to find that. So we're starting at B, C, D, E, and F. Okay, so now we can work within this smaller inset to see these correlations of carbon to hydrogen. So again, I'm going to practice drawing my lines straight down from the top and just moving them over so that they can correspond to whichever proton they go with. And again, trying to work as carefully with these as possible so that we make sure we're getting our correlations right. Luckily, we have the zoom for this one where we didn't for the COSY. So it may be a little bit easier to decide what's happening. Okay, so there's our hydrogens. And we'll do the same in red for the carbons. Get a nice straight line there and then move it as needed. Okay, it's really looking like plaid now, isn't it? It looks okay to me, even though 10 and 11 are very close together still. I think we're able to resolve them with this level of zoom. So let's go ahead and label these correlations with a letter number combination, and then we can get rid of this plaid because it's a lot to look at. So starting with B, it seems that B corresponds to 10, not 11, but 10. So B, 10 here. Then if we look at C, C seems to correspond to actually to 2 peaks, which is a little unusual, but not impossible. So this is a C13 peak there. We also have a C7 peak there. Interesting, interesting. Then we have D. D seems to correspond to 12. E seems to correspond to 11. And then F again has 2 correlation spots. This may be a little bit less surprising, but it looks like F correlates to 9 and 8. Okay, so I think that covers all of them. I'm going to go ahead and remove my annotation lines now so that we can have a little more visual breathing room. Ah, that's better. So now that we have all of these correlation peaks available to us, we can use them to kind of connect the puzzle pieces together. So now that we're done with that little zoomed in region, let's do the last couple of correlations that are here outside of the box. They're so small you might even forget about them because this inset seems to take a lot of precedence. So I'm going to draw down from A. It seems like this one aligns with A, and draw that over. It seems to correspond to carbon 1. So again, that won't always be the case, but in this case, it does make a lot of sense that our A hydrogen very, very far downfield, which we know is the aldehyde proton, would correspond well to our most downfield shifted carbon, which happens to be carbonyl carbon. So that correlation peak shows us that those two are directly attached. Again, we already knew that, So this isn't exactly a brand new earth-shattering piece of data, but it's good to have nonetheless. And then the other one here, again, will probably not be much of a surprise, that if we draw down from G and then draw over, we're going to get a correlation between G and 14, but we already probably could have guessed that as well, because G, we know, is going to be the furthest upfield is our CH2 protons, and 14 is the furthest carbon upfield, which means that that also corresponds to that sp3 hybridized carbon. All right, so those other pieces of data we kind of already had a good feel for, but these other ones may have been a little bit trickier to figure out without doing this HSQC analysis. So now that we've got all the pieces in place, there are a lot of different ways that you could go about starting to try to put these pieces together. What I'm going to do in this video is go back to the protons, because I think there's a lot to be said about neighbors and splitting, and looking at some of those COSY peaks to see who's got to be next to who. And then maybe we can kind of fill in some of the blanks about the carbons afterward. Let's try that. So before I go all the way back to the one-dimensional NMR, I want to revisit the COSY and take these cross peaks that we're seeing and just tabulate them. So in order to get the most out of this data, you don't have to necessarily be sitting and staring at it forever. What I can do is just on the side here, write that B correlates to G, E correlates to G, E correlates to F, D correlates to F, and B correlates to C. And now that I have this COSY information, we can take that small annotation and copy it so we can put it somewhere on our proton page, and just keep it in mind for when we're thinking about what possibly correlates to what else. It's a little crooked, but I think we'll leave it there for now. Okay, so let's start putting in some of these labels for the things that we're pretty sure about, and start thinking about splitting and neighbors to help us figure out the rest. So we are already very confident that this labeled hydrogen out there is A, that's our aldehyde proton, and we're pretty confident as well that these protons are Hg for our CH2. As I alluded to at the end of the 1D proton section, we can think about these two Hg protons as a sort of a handle to help us get started with walking around the rings to find their neighbors. So we know that both of the HGs are going to be split by two different things, and that's here. So G is split by B, and G is also split by E. So that means this proton here is either B or E, and this proton here is either B or E. So how will we decide which one is which? This is where we want to take some time to look at splitting and think about neighbors. So let's start with proton B. The signal for that is right here. So we said that that corresponds to one hydrogen. That doesn't really help us because in both cases we're looking at a single hydrogen, but the singlet nature of it does tell us something. So if we think about proton B has to be in a place where it would pretty much show up in the 1D NMR as a singlet. Like I said, it looks a little lumpy, but I can't tell what's going on there. It essentially looks like a singlet. So if we compare this position to this position, I think we'll find that this position here is the only one that doesn't have any direct neighbors. When we start to fill in a little bit more about the other protons, we can't forget about that proton, which is immediately adjacent to our other position. So for that reason, I think we can rule that position out. That can't possibly be B, because B must be a singlet. If we look at E, E is not a singlet. So this proton here is much more likely to be proton E, and this one, still circled in purple, is much more likely to be proton B. So I think that's a pretty good start as far as, oh, okay, we're starting to put some labels in, and we already have a hint to think about, oh, if this is HE here, we know it has to be split by this neighbor. So if we think about where we see the splitting in our COSY, we hopefully can figure out what that neighbor is as well. So looking at the COSY, we know that proton E is split by proton G. That's what we just figured out, but it is also split by proton F. So this must be proton F. But you're kind of asking yourself, maybe when we're looking at the signal for F over here, it's a 2 hydrogen signal, not a 1 hydrogen signal. So what's going on there? Also, thinking back to our HSQC data, we saw that proton F seems to correlate both to carbon 8 and carbon 9. So something a little bit strange is going on there. If we look back at our protons in our structure, we have to have 2 protons that fit into the signal F that must be on 2 different carbons, 8 and 9. So this must be that 2 protons F are not exactly the same, but they're similar enough that they come out at almost exactly the same chemical shift. So because of that, I have to think the other proton here adjacent as well must also be F. Well, it's not exactly the same as F, so let's call that F prime. Since we don't really know which one is which here in this kind of lumpy peak situation, we'll call this both F and F prime because they're not exactly the same, but they're very, very similar to one another. So with that assumption made, we can continue to look at our data from the COSY to say, oh, okay, well, if F and F prime are very similar, but they're not exactly the same, perhaps one of these COSY relationships is F prime correlating to another proton D. So if we think about that, the only other logical remaining proton is at this position here, and that could be HD. Let's look back at our one-dimensional spectra to see if that seems to make sense. D does correspond to only one proton and is split into a doublet by one neighbor. I think that adds up for the position that we've put it at. Now, we have only one other signal to contend with, and that is C. That's the only one that's not labeled on our drawing so far. C is another kind of question because it's a singlet for 2 hydrogens, and we don't have any hydrogens that are exactly the same. And it's also weird that it's a singlet, right? Because in our F and F prime case, sort of made sense that, they're not exactly the same, but they're close. So that's why you see kind of a funny splitting because of all of the neighbors. And then it's kind of a broad peak that covers a wide range of hertz, much more wide than, say, a singlet like C. But the only other positions that are left are on that other benzene ring that has the aldehyde on it. So possible that they go there, but is there any other evidence that would make this make sense? I think there is. If we look at our last correlation from our COSY info, we can see that B correlates to C. And we don't really see that in the one-dimensional spectra, right? Because they both pretty much look like singlets. But I think this makes a lot of sense based on the previous examples that we've done, where we looked at longer range coupling and splitting over a benzene ring scaffold. We could get a 4-bond coupling from B to this position here for a smaller number of hertz, say on the order of 1 to 3 hertz, that may not show up very well in our one-dimensional NMR, but it seems like the COSY is picking it up. So that could definitely be proton C. Again, we come to the problem that we had with F, that C is a singlet for 2 hydrogens. Going back to the HSQC, C also correlated to 2 different carbons. So I think we have a very similar situation for C that we did for F, where we have 2 protons here and here that are fairly similar. So they're showing up at very similar chemical shifts, but they're not exactly identical. So they sort of seem like they wouldn't be the same, but they're showing up as the same in our one-dimensional NMR. So we'll call this C and C prime. If we had a little bit more data, say an HMBC spectra, we'd be able to find a little bit more out about protons F and F prime and be able to more definitively say which one is which. For instance, we'd be looking for proton F to have a 1, 2, 3 bond coupling to the carbon that's attached to HD, which we could tell from our HSQC data. In the absence of HMBC data, we can just leave it as F, F prime, and C, C prime, because we don't have enough data to differentiate between the two. With these preliminary assignments of which hydrogens are at which positions, I think we can take these and then think about our HSQC data to start assigning which carbons are at which positions. So let's copy our annotations here and take them down to our HSQC sheet and start taking a look at those carbons. All right, with our protons transferred over, now we can start assigning some carbon numbers. So let's go back to red, and because these carbon numbers get fairly high and there's a lot of carbons to fit in, I'm going to change my pencil size to be a little bit more fine point. Again, we can just start with some of the easy low-hanging fruit to get ourselves warmed up. We know that carbon 1 is our aldehyde carbon, so we can go ahead and label that straight away. And we know that the CH2 is carbon 14. With those two taken care of, now we can look at the rest of the correlations that are in our little zoomed in region. So start anywhere. I'll just start with B. B is correlated to carbon 10, so that is probably carbon 10. For C and C prime, we know that one of them has to be on carbon 13 and one of them has to be on carbon 7, but we're not exactly sure which. Given the very big difference in the chemical shift of carbon 7 and carbon 13, I think we can allow ourselves to make a guess about which one of those is going to be a more de-shielded and therefore downfield signal. So looking at carbon 7, it's shifted much further downfield than carbon 13, which means it must be at a position that is strongly withdrawn because of a group that is close by to it. So between C and C prime, I think we want to assign that carbon 7 to be right here next to our aldehyde group coming off of the benzene ring. Why is that? You can picture it with a resonance form. Now, unfortunately, we have the opposite resonance form of the benzene ring that I would like to demonstrate this, but I'll show you how both carbon 7 and 10 are going to be relatively withdrawn due to the nature of this electron withdrawing aldehyde. It is all due to resonance. We can bring that double bond outside of the benzene ring and go up to a negatively charged oxygen, which demonstrates the withdrawing nature of the carbonyl group on a benzene ring. So position 10 and position 7 are going to be more withdrawn than, say, position 13, which must be here, which being meta to that withdrawing group is going to be much, much less affected by its electron withdrawing nature. Okay, so we've got an idea between those two, which one is which. Let's continue on. Proton D was correlated to carbon 12, E was correlated to 11, F was correlated to both 8 and 9. So again, without a little bit more data there, it's going to be tough to tell the difference between 8 and 9. You could definitely do it. It would be much easier to do if we had that HMBC data. Without that, I'm happy for you for this example to say, oh, hydrogen F and F prime and carbon 8 and 9 could be interchanged. We don't really have enough data to easily be able to tell between the two. So we're pretty much there, right? Well, some of you maybe are wondering about the few carbon numbers down here that went totally unused. Where are those carbons? We didn't see any HSQC correlations for those, so what happened to them? They didn't just disappear. If you look on our structure, you'll be able to probably note a couple of places where we haven't filled in any carbon labels, specifically at these positions here, which are all quaternary carbons. Because they're quaternary, they don't have a hydrogen to carbon direct correlation, so we don't see them show up in our HSQC. With a little bit more help, again, from something like an HMBC, we'd be able to assign them pretty clearly. But for the purposes of this assignment and not having an HMBC, don't worry about it. So for the purposes of this exercise, we wouldn't ask you to give specific positions for carbons 2 through 6 because you just don't really have enough information to come up with the exact correct structure. Again, you could do some resonance analysis to say, oh, okay, based on the electron withdrawing nature of the aldehyde, I would expect these carbons to be slightly upfield or downfield relative to one another. For this example, we'll just say that 2 through 6 are our quaternary carbons that are unlabeled. For your post-lab assignment, you will have a few signals that are going to be relatively similar to one another and difficult to differentiate between. Since that is the case, we won't be asking you to do a detailed analysis to try to pick them apart. We're more looking for you to label the absolute most obvious and interesting differences of protons and carbons. So that's it. We've done it. Take a second to give yourself a pat on the back for getting through this one. This is the first full spectral assignment that you've walked through. Even with me walking you through it, it may not be easy or feel like it's going to come naturally to you, but I promise practice will make it a lot easier. So good for you for getting through this one. We'll have one more to go through that has a little bit more complexity and maybe some stereochemical considerations to talk through as well, that should really set you up in a good way to be able to tackle your post lab. If you have any questions about this, stop by my office hours or leave a comment. Thanks for watching.